These are basic diode problems and half and full wave rectifier problems. Okay, so for 7b and 8b, these are both regarding the same circuit diagram, so I'm going to work them together. So 7b is you're asked to determine whether the silicon diode in the circuit is forward biased or is it reverse bias. So this is our silicon diode, and as we can see, you need to determine the direction of current and where the positive terminal is versus where the negative terminal is of your voltage source, and just whatever the voltages are at those different points. So in order for the silicon diode to be forward biased, we would need a difference of 0.7 volts from the anode side to the cathode side. The anode side is actually at ground, but we notice that the source voltage on the right hand side here is in the direction where it's feeding current this way. So from ground over here, we're going to have a drop at some point of 100 volts before we get to this point here. So that indicates that we should be at a lower voltage than 0 on the cathode side of the silicon diode. So for that reason, the silicon diode is forward biased, which means there should be current through the diode. Okay, and then 8b, we're actually asked what the voltage is across the diode, and for a silicon diode, VD should be 0.7 volts. Okay, now I'm going to take this a step further. We weren't asked to find the current through the diode, but we might as well do that. And so this is a good review of our circuit analysis techniques. So if I'm going to find the current through the diode is actually in series with the 560 ohm resistor. So the diode current is actually the same current as IR, the current through the resistor. So what we have here, if we look at Kirchhoff's voltage law around a closed loop, we know that we would have, that would be a drop of 0.7. So in that clockwise direction, we're going to see a drop of 0.7 volts, and then we're going to see a rise of 100 volts, and then we see a drop of whatever this VR is. And then when we get back to where we started, around that loop, that has to equal 0. So this tells us that VR, if we move it to the right-hand side, it becomes positive. VR would actually be 99.3 volts. It's 100 minus that 0.7. So if we want to find the current through that resistor, it would be the voltage drop across the resistor divided by the resistor. That's Ohm's law. So 99.3 volts divided by 560 ohms of resistance would give us about 177 1/3 milliamps. And so that would also be the current through the diode. So of course you want to make sure your diode can handle that amount of current. Again, that wasn't asked in the problem. I just thought it would be interesting to actually go over that. Okay, so for 7C, we have a 30 volt source and a 1 kilo ohm resistor here, 1.5 kilo ohm resistor here, 4.7, and another 4.7. And we want to determine if this silicon diode is forward or reverse biased. Now, again, we're looking at the source, and we see that we're applying a positive 30 volts. So at this point in our circuit, if we would measure with our digital multimeter, we would be measuring plus 30 volts. Now, it's a good indication that we would have that dropped across the rest of the circuit, and it's very likely that we would see that 0.7 volt drop across the silicon diode. So in this case as well, the diode is forward biased, meaning it would be conducting current. Okay, and then for 8C, we're asked again what the voltage is across that diode. Again, if it's a silicon diode, we should see 0.7 volts there. Okay, now for my friends who might have learned mesh analysis, we could actually find the current through that silicon diode. I'm gonna use the format approach to mesh analysis. If you haven't used mesh analysis, you haven't taken that in your circuits class, you can skip this part, or you can just kind of follow along and see if you understand what we're doing. And if not, just skip it. It's not necessary, really. That wasn't asked as part of this question. But if you're curious, you can, of course, watch. If you have done mesh analysis, see if you can follow along with this. So what I have here is a circuit with two meshes here and here. I'm going to call this mesh my I1 mesh and this one my I2 mesh. And what I'm going to do is then write my equations for each mesh current. Okay, and remember what we're doing is we need two equations because we have two unknown currents here, and then we're going to do solve them simultaneously to find the answer that fits both equations. So for the I1 equation, what I'm going to do is for the I1 term, I'm going to sum all of the resistances connected to this mesh. So that's going to be the 1K, the 1.5K, and the 4.7. So when I sum all of those resistors, I get 7.2 K times I1. And then the I2 term, I'm going to subtract anything that's connected to both I1 and I2. And as you can see, that is just the 4.7 right here. So that's going to be minus 4.7K times I2. Let me make that just a bit bigger here. Minus 4.7K times I2. And then on the right-hand side, that will be any voltage sources that we see in that mesh, and that would be 30 volts. And in the clockwise direction, we're adding 30 volts. So that means on the right side of the equation, we're going to add that 30 volts there. Okay, so for the next equation, I'm going to focus on the mesh over here. And again, I'm going to sum all of the resistances connected in this particular mesh. That's the 4.7 here and the 4.7 here. And that's going to be my I2 term because that's the mesh that we're in. So together that would make 9.4 kilo ohms times our I2. And that's going to be added. And we're going to subtract the I1 term, and that's going to be including any resistor that's connected to both I1 and I2, which again is this 4.7K. So minus 4.7K times I1. Just to stick with that convention, I'm going to change that to blue. No, that should be a negative. Sorry. Make sure you've got your signs right. And then for the right-hand side, that's going to be any voltage sources that I encounter in that mesh. Now, for the practical diode, we're looking at that as if it's a voltage source. And it's 0.7. And in the clockwise direction, that is a drop. So I'm going to use that as minus 0.7. Now what we do is we plug this into our simultaneous equation solver. You could also do substitution if you wanted. We could use a matrix to do it. Typically, using your calculator is the best way to go. And then we solve for I1 and I2. So I1 would be 6.11 milliamps. I2 would be 2.98 milliamps. And then we can find whatever we are looking for in our particular circuit. So what I find is that I2, if you look at where this mesh current actually does go in the circuit, I2 is through this path right here, which actually is our diode current. So that is actually the diode current. So we could find that, and if you wanted to work back through, you would see that these two currents actually do cause the correct voltage drops, and it would work out. I just wanted to throw that in there for those of you who understand mesh analysis and wanted to look at that as a review. But that was not asked of you, so you don't need to do that. Okay, let's talk about half rectifier problems. So here I have problem 11, and we're asked to draw the output waveform for each circuit. So I'm going to draw the output waveform here. So for the top here, we see that the current will be allowed to flow when the voltage is positive, at least 0.7 volts more. At least 0.7 volts across that diode will turn the diode on, and it will allow us to get our output voltage on the other side. So what that means is from T1 to T2, we're actually going to see the same. We're actually going to see exactly what we have here on the output. And I say exactly with one minor change, and that is that we're going to have 5 volt, our peak is going to be 5 volts minus that 0.7, because we're going to see that drop before we get to the output voltage, and that would be 4.3 volts. Now from let's change the color here maybe. So from T2 to T3, that is going to reverse bias the diode, which will cause an open circuit here, right? So nothing will get to V out, which means V out will be at 0 here from T1 to T3. Okay, and then when we get back between T3 and T4, let's use yet another color here. Okay, T3 to T4. We see that we are forward biasing the diode again, and we will, of course, see another peak again at that 4.3 volts. Okay, so 12 is asking what the peak inverse voltage would be across each diode. And the peak inverse voltage for this particular problem, so 12, uses the same circuit diagrams as 11. So the peak inverse voltage is simply the peak of the input signal, which would be 5 volts. Okay, and it's usually safe to maybe go about 20% above that. In actuality, let me go ahead and color this in just so you see kind of what that looks like. Okay, let's look at 11b. So 11b is pretty much the same problem, but this time with the diode reversed. And what's going to happen here is from T1 to T2, we're going to see that the diode is reverse biased, which means it's an open circuit between the input and the output. So from T1 to T2, we would simply see a 0 output, no voltage on the output. And then for T2 to T3, of course, we see here that the diode would actually be forward biased or on, so we would see at the output what we have on the input, and that would actually mirror what we see here at the output. And then at T4, from T3 to T4, from T3 to T4, we have reverse bias the diode again, which opens it up between the input and the output, and so it would be 0 there as well. Okay, so 12b is asking about the peak inverse voltage, and what we have here is, again, the peak inverse voltage would be the peak of the input signal, which in this case is 50 volts. And I forgot to mention that the negative peak here would be, remember you've got this 0.7 volt drop across the diode, so it would be minus 50 plus 0.7 on its way to the output, which would be minus 49.3, as we have dropped that 0.7 volts there. Okay, so that's number 11. Now, number 15 is really just a question about a transformer. So the question in number 15 asks, we have a power supply transformer that has a turns ratio of 5 to 1. That means we have 5 times the number of turns on the primary side as we do on the secondary. Let me write turns here as well. Okay, so for every 5 turns on the primary side, we only have 1 turn on the secondary side. That is what we call a step-down transformer. So that's going to step our input voltage down by that ratio. So if the secondary, what is the secondary voltage if the primary is connected to a 120 volt RMS signal? Okay, so the secondary voltage would just be the primary side divided by 5, because it's 5 to 1, or 20% of the primary. So 120 divided by 5, that would give us 24 volts RMS on the secondary. Okay. Now, if you wanted to find the peak for the secondary, which we would be looking at with an oscilloscope, you could do that. So the voltage of the secondary peak would be the RMS voltage divided by 0.707, or the RMS times the square root of 2. Those are the same thing. Again, I like to include both because you'll see both if you search for this online. So 24 divided by the 0.707 would be 33.95 volts peak for the secondary. Okay, so if you were looking for RMS, that would be 24. If you're looking for peak, that would be about 34. And remember that peak for 120 volts RMS is around 169.7. So a fifth of that should be around 34 as well. Okay, now let's look at the longer problem. This is, first of all, we're asked, what is the circuit shown here? Well, we see that there are two diodes that allow for the positive portion of our waveform and the negative portion of the waveform to go through to the output. So what that tells us is we have a full wave rectifier. I'll put V out over here. And also we see that in the middle we have this center tap going to ground. So that tells me that this is a center tapped full wave rectifier circuit. Okay. What is the total peak secondary voltage? So we're just looking at the secondary voltage here, and we see that we have a 4-to-1 ratio for that step-down transformer. And so we can do this a couple ways. We could find the peak input voltage on the primary side and then divide by 4 to find the peak at the secondary. Or we could do find the RMS of the secondary using the RMS that we're given here for the primary, and then find the peak after that. So it kind of depends on how you want to do this. But let's find the peak of the primary first. I'm going to keep this in green. So the primary peak, actually, let me write this differently. We want the V peak of the primary side. Okay, of the primary side. So that is going to be the 120 volts RMS divided by 0.707, which is 169.7 or so V peak. And then the V peak of the secondary will be V peak of the primary side divided by 4. So 169.73 divided by 4, and we get 42.43 volts peak, and that is, of course, the secondary peak voltage. Now, that is measuring from this side to this side of the transformer output. It is not using the center tap. So the center tap basically will split this 42.43 into two different waveforms up here. So we'll have one half of the waveform here, the other half of the waveform here. So the center tapped V peak secondary tapped will be half of V peak of the secondary. So 1/2 of the 42.43 will give us 21.21 or 22, something like that. Okay. So that's what we would see as the peak for just the signal going to D1 or just the signal going to D2. So we're going to sketch the output waveform across RL. Now this is going to be a full wave rectified output. So what we would see is for every half cycle of our sinusoidal waveform, that's going to become a positive peak in our output. And then the output here is going to be the 21.22 volts minus the 0.7 that we see as a drop on each side of the diode. So that means our peak there would be 20.5. I got 20.52, and that'll be our peak of the output. And what is the peak current through either diode? So if we have a V out, the peak is at 20.52 volts. That's the highest the voltage is going to be. Then if we divide that by the 1K, that'll give us the peak current. And that current is what we'll see through each diode. Because on the positive going side of our signal, D1 will be supplying the current here. On the negative going side, D2 will be supplying current there. So only one of them will have that current at one time. So the peak current will be V peak over R. Again, Ohm's law here. So 20.52 over the 1 kilo ohm resistor, or 20.52 milliamps. And then what is the peak inverse voltage for either diode? Now for the center tapped, keep in mind that we're always going to see some kind of reverse bias against each of these diodes through each portion of the circuit. So the total we're going to see for the peak inverse voltage needs to be 2V P out plus 0.7. And you can use Kirchhoff's voltage law to kind of figure that out. But we've got 2 times 20.52 volts peak plus 0.7. So our peak inverse voltage needs to be at least 41.73 volts. So we would look on the data sheet for the diode for that. And those are the practice problems.